Welcome back, and in this video, which is part 2 of my DNS mini-series, I want to cover some of the reasons why DNS is structured in the way that it is. Why do we need lots of DNS servers? Why isn't one enough? Additionally, at the end, I'm going to introduce some key DNS terms and then introduce the hierarchical structure of DNS. So let's jump in and get started. Now, there are a few main problems with just having one DNS server or even a small number of servers. It's important that you understand these reasons because it will help you understand why DNS is architected in the way that it is. First, there's the obvious risk problem. A small group of bad actors could attack the DNS infrastructure and without much effort prevent it servicing genuine requests, and that's something that we have to avoid for critical systems on the internet. Also, we have a scaling problem. Almost everyone who uses the internet globally uses DNS. This represents a massive and growing load on the system. A single server or a small group of servers can only get so big. If every access is being made against one or a small group of servers, no matter what information is being requested, the system cannot scale. Now, additionally, DNS is a huge database. Current recent estimates predict that there are around 341 million domains such as Netflix.com, Apple.com and Twitter.com, and each of those domains might have many records, tens, hundreds, thousands or even more records in each of those domains, and so this represents a huge data volume problem. We start with the amount of data but then also need to take into consideration updates to that data as well as consistency issues. And all of that data is accessed by anyone using the internet on a constant basis. Now, we can address the risk problem by creating more servers, each of them storing an exact copy of the same DNS data. The more servers we have, the more load can be tolerated against those servers, and the less risk of attackers managing to take down the entire platform. But this method doesn't really do anything about the scaling problem. If every user of DNS communicates with any of the servers at random, it means that every server needs to hold the complete DNS dataset, and this is a huge amount of data. It's a huge global scale monolith, and this is something that we need to avoid. Ideally, we also need to have the ability to delegate control over certain parts of the DNS dataset to other organisations so that they can manage it. So UK domains, for example, should be managed by a UK entity, US domains should be managed by somebody in the United States, .gov by the US government, .au by an organisation in Australia, and so on. And for this, we need a hierarchical structure. Now, I'm going to be talking about this fairly soon, but for now I need to introduce some DNS terms. Now, I need you not to switch off at this point in the video. I'm going to be using some bullet points. I hate bullet points, but these are worth it, so please stay with me. The first term that I want to introduce is a DNS zone. Think of this like a database. So we have Netflix.com, and that's the zone. Inside that zone are DNS records, for example, www.netflix.com, as well as many others. Now, that zone is stored on a disk somewhere, and that's called a zone file. Conceptually, this is a file containing a zone. So there's a Netflix.com zone file somewhere on the internet containing the Netflix.com zone and all of its records. We also have DNS name servers, known as NS for short, and these are DNS servers which host one or more zones, and it does so by storing one or more zone files. It's the name server or name servers for the Netflix.com zone which can answer queries that you have about the IP address of www.netflix.com. Next, we have the term authoritative, and this just means that for a given domain, this is the real or genuine, or to put another way, the boss for this particular domain. So there are one or more name servers which can give authoritative answers for www.netflix.com. These can be trusted. They're the single source of truth for this particular zone. And we also have the opposite of this, which is non-authoritative or cached, and this is where a DNS server might cache a zone or records to speed things up. Your local router or internet provider might, for instance, be able to provide a non-authoritative answer for learn.cantrell.io or youtube.com because you visited those sites before, but only my name servers can give an authoritative answer for learn.cantrell.io. Now that you know those terms, I want to introduce the architecture of DNS, so its hierarchical structure. And don't worry, this is high level only. I'll be covering the detail of how DNS works and how it's used in a follow-up video. So at this point, you know why a single DNS server is bad. You also know why having many DNS servers is bad if they just store the same monolithic set of data. And you understand a few important DNS terms. What I'm going to step through now is a hierarchical design, which is the way that DNS works. Using this architecture, we can split up the data which DNS stores and delegate the management of certain pieces to certain organizations. Splitting the data makes it easier to manage and also splits the load. If you're doing a query on Netflix.com, you generally won't have to touch the infrastructure for Twitter.com. Now, DNS starts with the DNS root, and this is a zone like any other part of DNS, and this zone is hosted on DNS name servers also just like any other part of DNS. So the DNS root zone runs on the DNS root servers. The only special element of the root zone is that it's the point that every DNS client knows about and trusts. It's where queries start at the root of DNS. Now, there are 13 root server IP addresses which host the root zone. These IP addresses are distributed geographically, and the hardware is managed by independent organizations. The Internet Corporation for Assigned Names and Numbers, or ICANN, operates one of the 13 IP addresses which host the root zone, and others include NASA, the University of Maryland, and VeriSign. So to be clear, these organizations manage the hardware for the 13 DNS root server IP addresses. In reality, each of these 13 IP addresses represents many different servers using Anycast IP addresses, but from DNS's perspective, there are 13 root server IP addresses. Now, the root zone, remember, this is just a database. This is managed by the Internet Assigned Numbers Authority, known as IANA. So they're responsible for the contents of the root zone. So management of the root zone and management of the root servers which host the root zone is different. Now, the root zone doesn't store that much data. What it does store is critical to how DNS functions, but there isn't that much data. The root zone contains high-level information on the top-level domains, or TLDs, of DNS. Now, there are two types of TLD, generic TLDs such as .com and country code-specific ones such as .uk and .au. IANA delegates the management of these TLDs to other organizations known as registries. Now, the job of the root zone really is just to point at these TLD registries. So IANA delegate management of the .com TLD to VeriSign, meaning VeriSign is the .com registry. And so, in the root zone, there's an entry for .com pointing at the name servers which belong to VeriSign. Now, .com is just one TLD. There are other entries in the root zone for other TLDs, and other TLDs could include .io, .uk, and .au, and many more. Because the root zone points at these TLD zones, they're known as authoritative, the source of truth truth for those TLDs. This process where the root zone points at the name servers hosting the TLD zones, it establishes a chain of trust within DNS. So to summarise, the root zone is pointing at the name servers hosting the TLD zones run by the registries, which are the organisations who manage these TLDs. So VeriSign will operate some name servers hosting the .com TLD zone, and the root zone will have records for the .com TLD which point at these .com name servers. The .com zone, which is just another DNS zone, also contains some data, specifically high-level data about domains which are within that .com TLD. For example, the .com TLD zone contains some records for twitter.com and netflix.com, so records for domains which exist inside the .com zone. The TLD only contains this high-level information on domains within it, for example, netflix.com. It doesn't contain detailed records within these domains, for example, www.netflix.com. All the TLD contains is information on the domain itself. Specifically with this example, a set of records for netflix.com which point at the name servers which host the netflix.com zone. Now it will also contain records for twitter.com which point at the name servers which host the zone for twitter.com, as well as records for every other domain within the .com TLD. Now these name servers, because they're pointed at from the layer above, they're authoritative for the domains, the zones that they host. So the name servers for netflix.com are authoritative for netflix.com because the netflix.com entry in the .com TLD points at these name servers. Now these name servers host the zone for a given domain, for example netflix.com. This means the servers host the zone file which stores the data for that zone. At this level, the zone contains records within netflix.com, so www.netflix.com, which points at a set of IP addresses. And because the zone and zone files are on these name servers, and because these name servers are authoritative for the domain, these zones and zone files are also authoritative. Now don't worry about understanding this in detail. In the next video I'm going to be walking through how this works in practice. For now, all I need you to understand is that each layer of DNS, from the root, the TLDs and the domain name servers, they store only a small part of the DNS database. The root zone knows which name servers the .com zone is on, the .com zone knows which name servers netflix.com zone is on, and the netflix.com zone contains records for the netflix.com domain and can answer queries. So this is the hierarchical architecture of DNS, and in the next video in this video series I'm going to be stepping you through the flow of how DNS works and discussing the architecture at a more technical level. But at this point that's everything I'll be covering in this video, so go ahead and complete the video, and when you're ready you can join me in the next video of this series.